The surface of a red giant glows at temperatures between 3500 and 5000 Kelvin, producing a warm, reddish hue. Unlike O-type stars, which radiate fiercely from compact surfaces, red giants radiate gently but immensely over huge volumes. A typical red giant's radius might stretch from the Sun's position all the way out to Mercury or Venus. As the star expands, its luminosity increases dramatically, sometimes to hundreds or thousands of times its original brightness. Yet the energy comes not from increased core burning, but from the hydrogen-burning shell wrapped around the contracting core. Inside the core, helium accumulates but cannot ignite because degeneracy pressure, not thermal pressure, supports it. This leads to one of the most extraordinary events in stellar evolution, the helium flash. In low-mass stars, once the core temperature reaches around 100 million Kelvin, helium fusion begins explosively. The degeneracy prevents expansion, allowing temperature to skyrocket until the helium ignites in a matter of seconds. The star survives, but its structure changes dramatically. The core expands, the envelope contracts, and the star transitions to the horizontal branch. This helium flash is invisible from outside the star, but its consequences shape the later evolution of countless stars like the Sun. As red giants evolve, convection dredges up material from the interior, altering the star's surface composition. Elements born from nuclear reactions deeper within, carbon, nitrogen, and others, rise to the surface. These dredge-up events enrich the stellar atmosphere and eventually the interstellar medium when the star loses its outer layers. Stellar winds from red giants carry dust, molecules, and heavy elements into space, forming halos of gas around the star. Over hundreds of thousands of years, these winds can strip away much of the star's mass. The Sun will follow this path in about 5 billion years, swelling to engulf Mercury and Venus and possibly Earth. Its surface will cool, its luminosity will rise, its winds will bathe the solar system in dust and gas. Eventually, it will lose so much mass that its outer layers lift away entirely, forming a planetary nebula. The remaining core will shrink into a white dwarf, a stellar ember slowly fading over eons. Red giant branch stars are among the most common evolved stars observed in the night sky. They populate globular clusters, forming clear sequences in the heart-sprung Russell diagram. Their regularity allows astronomers to measure distances to galaxies and trace chemical evolution across stellar populations. They serve as cosmic chronometers, marking the ages of star clusters and providing clues to the formation history of the Milky Way. O-type stars and red giant branch stars sit at opposite ends of the stellar spectrum. One is young, violent, and massive. The other is ancient, swollen, and nearing its end. One blasts ultraviolet radiation into the darkness. The other glows softly in the red. One lives for millions of years. The other has endured billions. Yet both shape the cosmos. O stars through explosive influence, red giants through patient enrichment. Between them lies nearly the entire story of stellar evolution. They are among the final, most extravagant expressions of stellar evolution, stars in their twilight, yet shining with a peculiar vitality as they fuse the last available fuels in their interiors. Asymptotic giant branch, AGB. Stars represent the beginning of the end for low and intermediate mass stars. After billions of years of steady hydrogen burning, after expanding into red giants and experiencing the violent helium flash, these stars evolve into something grander and stranger. Their cores shrink into dense, degenerate spheres of carbon and oxygen, while their outer layers swell to enormous proportions. The entire structure becomes unstable, pulsating, shedding mass, producing dust, and forging new elements through nuclear reactions deep within. In their final million years, AGB stars fundamentally reshape the chemical richness of the galaxy, contributing some of the most important elements for life. An AGB star consists of a degenerate carbon-oxygen core surrounded by two active fusion shells. The innermost shell burns helium into carbon and oxygen, while a surrounding shell burns hydrogen into helium. These two shells alternate in dominance, leading to thermal pulsars, dramatic flashes of helium fusion occurring roughly every 10,000 to 100,000 years. These pulsars expand the star's outer layers, dredge up material from deep within, and create the spectacular variability that characterizes this phase. Some AGB stars grow so large that if placed at the center of our solar system, their surfaces would extend beyond the orbit of Mars or even Jupiter. The luminosity of an AGB star can exceed 10,000 times that of the Sun. Yet their surface temperatures remain low, often around 3,000 Kelvin or less, giving them a deep orange or red glow. Their atmospheres are cool enough for molecules to form: oxides, silicates, carbon compounds, and these molecules imprint distinctive patterns on the star's spectrum. But the most striking phenomenon associated with AGB stars is mass loss. Their outer layers, tenuous and weakly bound, are expelled by radiation pressure, stellar pulsations, and shock waves. Over time, the star loses a substantial fraction of its mass in a slow, dense wind, enriched with heavy elements forged within. This mass loss creates circumstellar envelopes, vast shells of dust and gas that surround the star like a cocoon. As these envelopes expand outward, they seed the interstellar medium with newly formed elements: carbon, nitrogen, fluorine, and the products of S-process nucleosynthesis, where slow neutron captures build heavier elements such as strontium, barium, zirconium, and even lead. The S-process is one of the galaxy's great sources of heavy elements, and AGB stars are its primary factories. Without AGB stars, the cosmos would lack many of the ingredients essential for complex chemistry, planet formation, and biology. The rhythmic pulsations of AGB stars give rise to remarkable variability. Mirror variables, the best-known class, brighten and fade dramatically over periods of months to years. Mira itself, Omicron Ceti, has been observed for centuries, its light curve a steady heartbeat of a dying star. These pulsations help drive mass loss, pushing material outward and creating shocks that allow dust to condense. Once dust forms, radiation pressure accelerates it outward, dragging gas along, a cosmic breeze that slowly strips the star clean. As thermal pulses continue, the star experiences repeated third dredge-ups, where convection carries newly synthesized carbon from the helium-burning shell to the surface. When enough carbon accumulates in the atmosphere, the star becomes chemically transformed. It turns into a carbon star, a rare and beautiful type whose spectrum and color betray the dominance of carbon-bearing molecules. These stars glow in deep ruby or garnet hues, their atmospheres rich in molecules such as C2, Cn, and CH. Their transformation represents one of the most evocative moments in stellar evolution, a star literally changing its elemental identity. Carbon stars are among the most visually striking objects in the sky. Their deep red tint comes from the absorption of blue light by carbon molecules, allowing only the warm red wavelengths to escape the thick, dusty atmosphere. Their mass loss intensifies as carbon dust forms, a soot-like substance that absorbs radiation efficiently and accelerates outward in the stellar wind. Carbon dust is a critical contributor to the galaxy's dust population, providing seeds for future planets, absorbing starlight in galaxies, and enabling molecular complexity in interstellar clouds. The creation of a carbon star reflects an internal struggle between carbon and oxygen. In main sequence stars, oxygen dominates. The CRO ratio is less than 1. But in AGB stars, repeated dredge-ups enrich the outer layers with carbon. Once the carbon-to-oxygen ratio exceeds unity, carbon-bearing molecules outnumber oxygen-bearing ones, and the star's entire chemistry shifts. Titanium oxide bands fade. Carbon bands flourish. The spectrum changes completely. Not all AGB stars become carbon stars. Those with initial masses around 2 to 3 solar masses are most likely to undergo enough dredge-up events to cross the CCEO threshold. More massive AGB stars experience hot bottom burning, where the base of the convective envelope becomes hot enough to convert carbon into nitrogen. These stars remain oxygen-rich and never become carbon stars. The interplay between dredge-up and hot bottom burning determines whether the star's final phase is dominated by carbon-based chemistry or oxygen-based chemistry. The dust produced by AGB and carbon stars eventually becomes part of planetary nebulae, the spectacular, multicolored shells of ionized gas that mark the transition from AGB star to white dwarf. The central star contracts and heats rapidly, flooding the previously ejected envelope with ultraviolet radiation that makes it glow. The shapes of planetary nebulae, round, bipolar, elliptical, or intricately sculpted, reflect the mass loss, rotation, magnetic fields, and binary companions of their progenitor stars. Carbon-rich envelopes produce distinctive molecular signatures and dust types, while oxygen-rich envelopes produce silicate dust. Even after the planetary nebula phase ends, the dust and molecules enriched by AGB evolution linger in the interstellar medium, becoming the raw materials of future star and planet formation. Carbon grains serve as nucleation points for the formation of ices in cold molecular clouds. These carbon-based ices, irradiated by cosmic rays and ultraviolet light, form progressively more complex molecules, organic compounds that eventually seed protoplanetary disks. In this way, the chemistry of carbon stars becomes part of the chemistry of life-bearing planets. Every world rich in carbon-bearing molecules owes part of its existence to ancient carbon stars that lived long before the planet itself formed. In the broader context of galactic evolution, AGB stars and carbon stars represent the transition from stellar processing to galactic enrichment. Massive stars contribute metals through supernova, but low and intermediate mass stars contribute through long, gentle shedding of enriched material. Both channels are essential. AGB stars build the foundations of interstellar dust, the cooling agents for collapsing clouds, and the building blocks for the next generation of stars. They are the cosmic artisans of heavy elements, weaving carbon into the galaxy and leaving behind the seeds from which new systems will grow. Their deaths are not violent, but transformative, turning interiors into exteriors, turning nuclear ash into usable matter, turning ancient stars into the dust that forms new suns. The AGB phase is a quiet supernova, a gentle yet powerful dispersal of the chemical wealth locked inside a star's core. And when a star becomes a carbon star, it becomes something more, a ruby in the darkness, glowing with the rich chemistry of future worlds, announcing that even in cosmic death, creation continues. They are the stripped, burning cores of once massive stars, objects that have shed their outer layers through winds so powerful that they reshape entire regions of space. Wolf-Rayet stars represent one of the final, most extreme phases of massive star evolution, where temperatures soar, radiation intensifies, and stellar winds reach velocities unimaginable in normal stars. A Wolf-Rayet star is not a gentle object. It is a furnace laid bare, a stellar skeleton irradiating the cosmos with fierce ultraviolet light and hurling material into space at millions of kilometers per hour. These stars are rare, short-lived, and among the most luminous in the universe. Each one is a signpost of imminent cosmic violence because Wolf-Rayet stars almost always end in catastrophic supernovae or even gamma-ray bursts. A Wolf-Rayet star begins its life as a massive O-type star, 15, 30, or even 60 times the mass of the Sun. During its main sequence lifetime, its powerful radiation strips material from its outer layers, exposing deeper and hotter regions of its atmosphere. For the most massive stars, this mass loss is continuous and dramatic, driven by radiation pressure and by instabilities in their outer envelopes. Over millions of years, the star transitions from the O-type phase to the Wolf-Rayet stage, revealing a core rich in the ashes of nuclear burning. Depending on the stage of evolution, the surface may be dominated by helium, nitrogen, carbon, or oxygen. These spectral fingerprints define the major subclasses: Wn, nitrogen-rich, Wc, carbon-rich, and Wo, oxygen-rich, each revealing a different phase of helium burning and mass loss. Wolf-Rayet winds are among the strongest known, often exceeding 2,000 kilometers per second. They blow off 10,000 Earth masses of material every year. These winds carve enormous bubbles into the surrounding interstellar medium, sweeping up gas and dust and compressing nearby clouds into arcs and filaments. The glowing shells around some Wolf-Rayet stars, such as the famous WR124 and its nebula M167, are relics of earlier mass loss episodes, stained with the products of nuclear processing. These nebulae are laboratories of enriched chemistry, filled with carbon and nitrogen synthesized deep inside the star before being blasted outward. The extreme temperatures of Wolf-Rayet stars, often exceeding 50,000 Kelvin and reaching up to 150,000 Kelvin, make them potent sources of ionizing radiation. In star-forming regions, they shape the evolution of neighboring protostars, evaporating circumstellar disks and altering the chemistry of molecular clouds. Their fierce radiation and winds, combined with the eventual supernova explosion, can trigger further rounds of star formation or disrupt entire clusters depending on the environment. Wolf-Rayet stars are also believed to be progenitors of long gamma-ray bursts, particularly those that rotate rapidly and retain sufficient angular momentum as they collapse. In such cases, when the core of a Wolf-Rayet star collapses, it may form a rapidly spinning black hole with an accretion disk that launches relativistic jets. If one of those jets is aimed toward Earth, we see a gamma-ray burst lasting tens or hundreds of seconds, the most powerful electromagnetic events in the cosmos. Many of the highest energy supernovae, including some hypernovae, are associated with Wolf-Rayet progenitors. Their deaths are as dramatic as their lives, leaving behind dense remnants, black holes, or neutron stars that carry forward the legacy of their colossal mass. And yet Wolf-Rayet stars do not live alone in the upper reaches of massive star evolution. Alongside them stand the majestic blue supergiants, some of the most luminous, visually striking stars in the night sky. Their blue-white brilliance belies their strange position on the Hertzsprung-Russell diagram. They are stars that have evolved off the main sequence, yet have retained their high temperature instead of expanding into cooler red supergiants. Blue supergiants are massive, often 10 to 40 times the Sun's mass, and they shine tens of thousands to hundreds of thousands of times brighter. Their surface temperatures range from 10,000 to 30,000 Kelvin, cooler than Wolf-Rayet stars, but still blisteringly hot. A blue supergiant forms when a massive star exhausts the hydrogen in its core. As the core contracts and heats, hydrogen burning moves into a surrounding shell, causing the outer layers to expand somewhat. But depending on rotation, mass loss, and internal mixing, the star may remain hot instead of cooling into a red supergiant. Some blue supergiants are transitioning toward the red supergiant phase. Others are moving back from it after intense mass loss. The star's path depends on its metallicity, wind strength, and internal physics. Some stars oscillate between blue and red phases multiple times, each transition stirring their interiors and altering their surface chemistry. Blue supergiants are luminous enough to serve as standard candles, distance markers for nearby galaxies. Their brightness is so overwhelming that they can be observed individually in distant spirals, making them important tools for measuring the scale of the universe. But their role in astrophysics extends far beyond distance measurement. They are key progenitors of supernovae, particularly the famous Type 2P and Type 2L events. SN 1987A, the closest supernova observed in modern times, was produced by a blue supergiant named Sanderlic 69-102. This shocked astronomers. It had been assumed for decades that red supergiants were the progenitors of Type 2 supernovae. SN 1987A proved otherwise, and its progenitor's unusual structure, compact, hot, and massive, sparked a re-examination of stellar evolution models. Blue supergiants possess powerful stellar winds, though not as ferocious as Wolf-Rayet winds. Their winds enrich the surrounding medium with helium, nitrogen, and other products of the CNO cycle. Their rotation plays a major role in shaping their evolution. Rapid rotation can mix the star's interior, dredging nuclear-processed material to the surface and altering its chemical signature. Some blue supergiants display anomalously high nitrogen levels, evidence of deep internal mixing. Others exhibit variability akin to smaller-scale pulsations, changes in brightness, radius, or temperature that offer clues to the internal structure of these colossal stars. The fate of a blue supergiant depends on its mass and history. Some evolve into red supergiants before exploding. Others evolve directly into Wolf-Rayet stars through mass loss. Still others may die as blue supergiants after brief but tumultuous post-main sequence phases. Whatever the path, their deaths mark some of the most spectacular supernovae in the universe, producing shockwaves that reshape their host galaxies and remnants that endure for millions of years. Together, Wolf-Rayet stars and blue supergiants represent two of the final luminous acts of massive star evolution, one stripped and furious, the other immense and elegant. Wolf-Rayet stars are the exposed cores, burning with unbearable intensity, shedding their identities layer by layer until nothing remains but a compact remnant. Blue supergiants are the swollen, brilliant giants, their physics driven by internal tension between shell burning and gravity. Both illuminate their surroundings with fierce radiation. Both sculpt the interstellar medium with powerful winds. Both end in the explosive dissolution of their cores. In their differences, they show the diversity of stellar destinies. In their similarities, they show the unity of stellar change. And in their deaths, supernovae, hypernovae, gamma-ray bursts, they write the next chapters of the universe's long story by creating the elements that will someday build planets, oceans, atmospheres, and life. They are among the largest stars the universe ever permits, swollen to colossal proportions in the final chapters of their evolution. Red supergiants, like the famous Betelgeuse in Orion, represent one of the last stable phases in the lives of massive stars. Stars born with 8 to 20 times the mass of the Sun, now expanded into titanic spheres with radii hundreds to over 1,000 times greater than their original size. Their surfaces glow with a deep, ruddy warmth, only a few thousand degrees above absolute zero, yet their luminosity outshines the Sun by tens of thousands of times because their physical scale is so vast. A red supergiant is not a quiet, peaceful object. It is a turbulent, convective, unstable monster, its atmosphere boiling, pulsing, and shedding material into space in a slow but relentless wind. The path to becoming a red supergiant begins once a massive star exhausts the hydrogen in its core. With fusion no longer generating enough internal pressure to counter gravity, the core contracts and heats while the outer layers expand outward. Hydrogen burning continues in a shell around the core, generating enormous luminosity. The temperature at the surface drops as the star inflates, pushing it into the red region of the Hertzsprung-Russell diagram. In this swollen state, the star becomes fully convective, churning violently from deep interior to surface. This convection drives enormous granules, bubbles the size of Earth's orbit, across the photosphere, creating brightness variations and chaotic turbulence. Betelgeuse, the most iconic red supergiant, demonstrates these dynamics vividly. Located roughly 550 light-years away, it has become one of the most closely observed stars in the sky. Its brightness fluctuates, sometimes dramatically, caused by both pulsations and massive convective cells rising and sinking through its atmosphere. In 2019, Betelgeuse dimmed to historically low levels, sparking global speculation that it might be on the verge of exploding as a supernova. Subsequent observations revealed the true cause. A massive ejection of material formed an opaque dust cloud, partially obscuring the star. This event confirmed what astronomers had long suspected, that red supergiants undergo episodic mass loss events far more violent than previously understood. The atmosphere of a red supergiant is an extended, tenuous envelope where dust, molecules, and even complex compounds form. Temperatures are low enough for silicates, alumina dust, and even carbonaceous grains to condense. The star's slow but persistent wind, accelerated by pulsations and dust-driven radiation pressure, carries this material outward into space. Over hundreds of thousands of years, a red supergiant sheds much of its mass that becomes part of the interstellar medium, feeding future generations of stars and planets. These winds create envelopes, arcs, and bow shocks around the star, visible in infrared observations as vast halos of material lit by the star's own radiation. Inside the core, hydrogen shell burning eventually gives way to helium fusion, the triple alpha process, followed by successive stages of heavier element production. The core contracts further, the star brightens again, and the outer layers may expand even more. Ultimately, a red supergiant reaches the limit of its existence when its core fills with iron, an element that cannot release energy through fusion. At that moment, the star's fate is sealed. A catastrophic core collapse ensues, triggering a Type II supernova, one of the most dramatic explosions in the cosmos. The star's lifetime of mass loss, turbulence, and instability culminates in a final act of destruction that will enrich space with oxygen, silicon, and other elements essential for rocky planets and living chemistry. Every breath of oxygen in Earth's atmosphere once came from such stars. If red supergiants are the swollen giants of stellar senescence, then yellow hypergiants represent a rarer, even more unstable phase. Stars caught in a precarious transition between hot and cool, shedding their mass at extraordinary rates. These stars, among the most luminous in the universe, occupy a narrow and volatile region of stellar evolution. Their luminosities rival or exceed those of red supergiants and blue supergiants, but their temperatures range between roughly 4,000 and 8,000 Kelvin, placing them in the yellow region of the HR diagram. Yet unlike stable stars of the same temperature, yellow hypergiants are in constant upheaval. They live on the brink of instability, suffering repeated eruptions, pulsations, and structural reorganizations as they struggle to maintain equilibrium. A yellow hypergiant is a massive star, typically 20 to 40 solar masses, that has already passed through the red supergiant phase. During its time as a red supergiant, it shed an enormous amount of mass, losing perhaps half its initial material to stellar winds. This mass loss affects the star's structure profoundly. As the core contracts and heats, the star may evolve bluos on the HR diagram, becoming a yellow hypergiant, a transitional stage on its way to becoming a blue supergiant or even a luminous blue variable. But this transition is dangerous. The star is moving through the yellow void, a region where stellar atmospheres are notoriously unstable. Opacity changes, envelope inflation, and turbulent convection create conditions in which the star cannot easily maintain hydrostatic balance. The result is extreme variability. Yellow hypergiants undergo episodes of dramatic mass loss, outbursts that can eject entire layers of their atmospheres. These eruptions are visible as sudden dimming or brightening, changes in spectral type, or even temporary disappearance behind a cloud of self-generated dust. One of the most studied yellow hypergiants, Rho Cassiopeiae, has experienced multiple such outbursts in the last century. During these events, its outer layers cooled drastically, forming dust and molecules that momentarily obscured the star. After recovering, the star heated again as it contracted, resuming its unstable attempt to transition toward hotter temperatures. These eruptions are driven by changes deep within the star. Instabilities in the hydrogen and helium ionization zones, regions where partial ionization creates opacity spikes, can cause the outer envelope to inflate and then collapse. When inflation goes too far, gravity can no longer restrain part of the atmosphere, and the star expels it in a violent, wind-driven pulse. Each eruption enriches the surrounding nebula with processed material, including nitrogen, oxygen, and complex dust grains. Some yellow hypergiants display multiple shells of ejected material, fossil records of centuries of instability. Unlike red supergiants, whose mass loss is steady and supported by dust formation, yellow hypergiants experience sporadic, eruptive mass loss. The winds can reach hundreds of kilometers per second, strong enough to strip material that was only loosely bound after years of red supergiant inflation. As the star loses mass, its evolutionary trajectory changes. Some yellow hypergiants may shed enough material to expose deeper layers and evolve into blue supergiants or even Wolf-Rayet stars. Others may oscillate back and forth, repeatedly crossing the yellow void until either mass loss or internal restructuring stabilizes them. The luminosity of yellow hypergiants is immense, on the order of several 100,000 to over 1,000,000 times the sun's luminosity. Their radiative output is so powerful that the star lives in a constant battle between gravity pulling inward and radiation pushing outward. In this delicate balance, even small fluctuations can lead to large-scale envelope upheavals. Eventually, a yellow hypergiant meets its end in a core collapse supernova. Whether it explodes as a yellow hypergiant, evolves into a blue supergiant first, or becomes briefly an LBV or Wolf-Rayet star depends on its mass and mass loss history. In every case, these stars leave behind remnants, neutron stars, or black holes, but their true legacy is the enriched material they cast into space. Red supergiants and yellow hypergiants together illustrate the unstable final years of massive stars. One expands to its physical limit, glowing cool and enormous. The other contracts and reheats after shedding much of its mass, struggling through a turbulent transformation. Both are transient. Both are evolving toward collapse. Both fill space with dust, molecules, and heavy elements, setting the stage for new stars, new worlds, and new chemistry. They are not quiet elders of the cosmos. They are roaring giants, ending their lives not by fading, but by burning brighter, larger, and more violently than ever before. They stand at the precipice of stellar instability, radiant and unpredictable giants whose lives unfold in alternating episodes of calm brilliance and cataclysmic eruption. Luminous blue variables, or LBVs, are among the most enigmatic stars in the universe. Massive, hot, and volatile, their outer layers held in a precarious equilibrium between gravity pulling inward and radiation pushing outward. They occupy the very uppermost reaches of the Hertzsprung-Russell diagram, shining hundreds of thousands or even millions of times brighter than the sun. Yet their lives are marked by deep internal tension, and their atmospheres can erupt without warning, shedding enormous shells of material that reshape their evolution and create massive nebula around them. An LBV typically appears after a massive star has already undergone significant evolution. After passing through the main sequence as an O-type star, after beginning shell burning, after developing interior instabilities that strain the structure of its envelope. While most massive stars expand into red supergiants, the most massive of all, those above roughly 30 solar masses, and especially those beyond 50, may instead cross into the LBV phase, where the combination of huge luminosity and high temperature renders their outer layers unstable. The star becomes prone to giant eruptions and outbursts that can transform it dramatically in a matter of months or years. The most famous LBV in the sky is Eta Carinae, a colossal binary system whose primary star is one of the most massive known. In the 1840s, Eta Carinae erupted in what became known as the Great Eruption, briefly becoming the second brightest star in the sky and ejecting several solar masses of material into space. That material formed the Homunculus Nebula, a pair of bipolar lobes expanding outward like the wings of an angelic explosion. This event did not destroy the star, nor did it mark its terminal collapse. Instead, it was a convulsive reorganization, an eruption driven by radiation pressure, opacity shifts, and deep internal instabilities. Many LBVs experience similar outbursts, though few rival Eta Carinae in intensity. These eruptions are thought to originate from the star's approach to the Eddington limit, the point at which radiation pressure becomes strong enough to lift material from the surface. LBVs live dangerously close to this limit. Even slight changes in temperature or ionization can cause portions of the envelope to inflate or be expelled entirely. Sometimes the events are mild, S-Doradus-type variations in which the star brightens and cools without losing much mass. Other times, they are explosive, the so-called giant eruptions that eject tens of thousands of Earth masses of material and mimic the brightness of supernovae despite the star remaining intact. LBVs enrich their surroundings with nitrogen, helium, and other products of deep internal fusion dredged up by mixing. Their winds are dense and slow compared to those of main-sequence O-type stars, and their nebulae often glow with intricate structure. Arcs, filaments, rings, bipolar lobes, and complex dust geometries sculpted by magnetic fields and stellar rotation. These nebulae are relics of past eruptions, expanding chronologies of instability that reveal a star caught in a prolonged battle with itself. The LBV phase may precede the Wolf-Rayet stage, or it may occur intermittently as the star evolves back and forth across the unstable boundary between different evolutionary regimes. The fate of an LBV depends on its mass. Some will shed enough material to evolve into Wolf-Rayet stars before collapsing. Others may explode as supernovae during or shortly after the LBV phase. In fact, some supernovae have been observed exploding from progenitors that exhibited LBV-like outbursts in the years leading up to their deaths. These so-called imposter supernovae reveal LBVs in their most volatile moments, illuminating a path to stellar death marked not by quiet aging, but by skyrocketing instability. Where LBVs mark the unstable twilight of stellar giants, Cepheid variables stand as rhythmic beacons of cosmic stability. Stars whose pulsars illuminate the structure of the universe itself. These stars, named after the prototype Delta Cephei, are evolved supergiants undergoing periodic expansion and contraction driven by an internal mechanism known as the key mechanism. Unlike LBVs, Cepheids do not erupt violently or shed massive shells of material. Their variability is precise, regular, predictable. Each cycle of brightness arises from a balance between opacity changes, temperature shifts, and the gravitational tug-of-war inside their envelopes. They are not unpredictable titans, but cosmic metronomes. A Cepheid variable typically arises in a star of 4 to 15 solar masses after it has exhausted hydrogen in its core and begun helium burning. As the star evolves across the instability strip of the HR diagram, its outer layers become susceptible to partial ionization of helium. When helium in the star's outer envelope is singly ionized, it absorbs more radiation and traps heat. This increases the internal pressure and causes the star to expand. As the star expands, the helium recombines, the opacity drops, and the radiation escapes, allowing the star to cool and contract. This cycle repeats with extraordinary regularity, producing a light curve with a distinctive rise and fall. The brightness variation of a Cepheid can be dramatic, sometimes a factor of 2 or more. The periods range from about a day to several months, depending on the star's mass, radius, and luminosity. Most importantly, there exists a precise relation between a Cepheid's pulsation period and its intrinsic luminosity. This period luminosity relation, discovered by Henrietta Swan Leavitt in 1912, transformed Cepheids into one of the most essential tools in cosmology. By measuring a Cepheid's pulsation period, astronomers can determine its absolute magnitude. By comparing that to its apparent brightness, they can calculate its distance with remarkable accuracy. Cepheids thus became the first reliable standard candles for measuring distances to galaxies beyond the Milky Way. Edwin Hubble used Cepheids in the Andromeda Galaxy to prove that it lay far outside the Milky Way, demonstrating that other galaxies exist. Cepheids became the stepping stones to the cosmic distance ladder, from nearby Cepheids to more distant type Ia supernovae, and from there to the expansion of the universe itself. Modern space telescopes like Hubble and JWST continue to use Cepheids to refine measurements of the Hubble constant, the rate at which the universe expands. In their internal structure, Cepheids exhibit layered envelopes, convection zones, and regions of partial ionization. Their pulsations cause temperature changes visible in their spectra, with the star appearing hotter when brighter. Their surfaces move in and out by millions of kilometers each cycle. Some Cepheids show additional modes or irregularities, but most remain astonishingly stable over long timescales, allowing precise calibration of cosmic distances. Yet Cepheids are not merely tools, they are evolving stars undergoing complex astrophysical processes. As they age, their periods change slowly. Some lengthen their periods as their envelopes expand, others shorten them as they contract. These period changes provide insights into the internal evolution of massive stars and serve as probes of stellar physics deep beneath the surface. LBVs and Cepheids form a striking contrast in stellar behavior. One class represents chaotic instability, the other ordered pulsation. One marks the volatile brink of stellar death, the other a rhythmic stage in mid to late stellar evolution. Yet both are luminous, both are large, and both are crucial to understanding the life cycles of massive and intermediate mass stars. LBVs shape their galaxies by shedding chemically enriched material and powering some of the brightest eruptions in the sky. Cepheids shape our understanding of the universe's scale, providing the means to measure cosmic distances and trace the expansion of space-time. Together, they demonstrate that stellar variability is not a mere curiosity, but a deep expression of the physical processes governing stars. Instability may signal death, pulsation may map the cosmos, but in every case, variability is nature's way of revealing the workings of stellar interiors. Through their brightness, their changes, and their influence, LBVs and Cepheids illuminate far more than themselves. They illuminate the architecture, history, and expansion of the universe. They are the ancient pulse of the galaxy, the heartbeat of its oldest stellar populations. R. Lyrae stars are veterans of the cosmos, old, metal-poor, low-mass stars that have survived nearly the entire history of the Milky Way. Born more than 10 billion years ago, they have passed through the main sequence, through the red giant branch and into helium burning. Now, they reside on the horizontal branch, oscillating rhythmically with a steadiness that makes them invaluable to astronomers. Though less luminous than Cepheids, R. Lyrae stars play an equally important role in mapping the structure of our galaxy and its satellites. Their regular pulsations, lasting only hours to half a day, are the flickering signatures of stars that emerged in the earliest eras of star formation. An R. Lyrae star, like a Cepheid, varies in brightness through the key mechanism, an instability rooted in partial ionization zones within its envelope. In R. Lyrae stars, the key driver is the partial ionization of helium. As helium absorbs energy and becomes more opaque, it traps radiation, raising internal pressure and causing the star to expand. When the outer layers expand and cool, the helium recombines, becoming transparent, releasing the trapped radiation and allowing the star to contract again. This constant expansion and contraction produces regular pulsations, typically with periods between 0.2 and 1 day. The light curves of R. Lyrae stars are sharp and distinctive, rising rapidly and falling slowly in a sawtooth pattern. Because R. Lyrae stars have nearly uniform intrinsic luminosities, far more uniform than Cepheids, they serve as reliable standard candles for measuring distances within the Milky Way and to nearby dwarf galaxies. Their absolute magnitude is roughly constant, around 50 times the luminosity of the Sun, which makes them perfect traces of ancient stellar populations. Wherever R. Lyrae stars are found, they reveal the presence of old, metal-poor stars. Globular clusters are filled with them, each cluster containing dozens or even hundreds of R. Lyrae stars flickering in unison across the sky. Their distribution across the halo of the Milky Way maps the galaxy's early merger history, tracing stellar streams from long-lost dwarf galaxies that were cannibalized by the Milky Way billions of years ago. R. Lyrae stars also provide insights into stellar evolution. They occupy a narrow band across the instability strip, with their pulsation properties depending sensitively on mass, temperature, and metallicity. The Oosterhoff classification, named after the Dutch astronomer Peter Oosterhoff, divides globular clusters into two groups based on the periods and brightness of their R. Lyrae populations. This classification reveals differences in the early star formation histories of clusters and remains a powerful tool for understanding the formation of the galactic halo. In every sense, R. Lyrae stars are fossils of the early universe, stars that have endured since the dawn of the galaxy, still beating with primordial rhythm, preserving in their pulsations the conditions of an era long vanished. But if R. Lyrae stars represent quiet, ancient endurance, then cataclysmic variables, or CVs, represent something far more turbulent: the explosive intimacy of interacting binary systems. A cataclysmic variable is a close binary star system in which a white dwarf accretes matter from a companion, typically a low-mass main sequence star, though sometimes a subgiant or evolved donor. The two stars are locked in an orbit so tight that the donor star fills its Roche lobe, spilling gas through the inner Lagrange point toward the white dwarf. This gas forms an accretion disk unless the white dwarf's magnetic field is strong enough to disrupt the disk and funnel the gas directly onto its poles. Whatever the geometry, the fundamental principle remains. The white dwarf continuously steals material from its companion, storing gravitational energy until the system releases it in brilliant, unpredictable bursts. CVs are among the most dynamic objects in the night sky. Their brightness can change dramatically, sometimes by factors of 10 or 100, over hours, days, or months. The disk accumulates matter in a slow, quiet state, gradually becoming denser and hotter. When the conditions reach a critical threshold, a thermal instability rapidly increases the disk's viscosity, sending gas spiraling inward. The result is a dwarf nova outburst, a sudden jump in brightness that lasts days before the disk cools again. These outbursts can recur every few weeks or months, producing a sawtooth pattern of regular explosions driven not by nuclear reactions but by changes in the physics of the accretion disk. Some CVs possess magnetic fields strong enough to transform their behavior completely. In polars, also called AM Hercules stars, the magnetic field of the white dwarf is so strong, tens of millions of Gauss, that it prevents the formation of an accretion disk. Instead, matter flows along magnetic field lines directly onto the magnetic poles, creating bright hotspots that pulse as the white dwarf rotates. In intermediate polars, the magnetic field partially disrupts the disk, creating a complex interplay between disk dynamics and magnetically channeled flow. The most dramatic CVs are the ones that undergo thermonuclear runaways on their white dwarf surfaces. When enough hydrogen accumulates and is compressed under the dwarf's intense gravity, it ignites explosively in a classical nova. The explosion does not destroy the white dwarf, and the system survives to repeat the cycle. Over thousands of years, a CV may erupt dozens or hundreds of times, enriching the interstellar medium with fresh material. In even more extreme cases, when the white dwarf's mass approaches the Chandrasekhar limit, continued accretion can push the star toward catastrophic runaway carbon fusion, producing a Type Ia supernova that completely destroys the white dwarf in a single, universe-shaping flash. CVs are astrophysical laboratories for studying accretion, magnetic fields, thermonuclear reactions, and binary evolution. Their flickering brightness reveals turbulence within accretion disks. Their eruptions reveal nuclear physics under extreme conditions. Their orbital period evolution reveals angular momentum loss via magnetic braking and gravitational radiation. Some CVs evolve toward shorter orbital periods until they reach a period minimum, where the donor becomes a degenerate object. Others evolve back toward longer periods as their donors cool and shrink. These evolutionary paths are crucial for understanding how binary systems interact, merge, or explode. And beyond their scientific importance, CVs are emotional reminders of the universe's violence on intimate scales. A white dwarf, the quiet remnant of a once shining star, devours its companion relentlessly, drawing material from it over millions of years. The donor star grows distorted, losing mass to tidal forces, eventually becoming a mere shadow of its former self. The system flickers, flares, erupts, and calms, then repeats the cycle until one of several possible endings: white dwarf cooling, binary merger, nova cycles that exhaust the donor, or a supernova that erases the system entirely. Our Lyrae stars and cataclysmic variables could not be more different. One class consists of ancient solitary survivors pulsing with quiet regularity. The other, intimate binary systems living in a state of perpetual instability. One is ordered, steady, predictable. The other, chaotic, eruptive, and volatile. Yet both illuminate essential truths about the cosmos. RR Lyrae stars show us the oldest skeletons of galactic structure, while CVs show us how stars interact, transform, cannibalize, and explode. Together, they form a study in contrasts, cosmic rhythm versus cosmic violence, each indispensable to our understanding of stellar evolution. They are the embers of dead stars, the long-lasting fossils of stellar evolution, glowing quietly after billions of years of internal fire. White dwarfs represent the most common final state of stars in the universe, including our own Sun. When a star of low or intermediate mass exhausts its nuclear fuel, it sheds its outer layers into a planetary nebula and leaves behind a dense core, a white dwarf, no larger than Earth, yet containing half the mass of the Sun or more. These stellar remnants are monuments to the quiet death of stars. Their light powered not by fusion, but by residual heat slowly radiating into the cosmos. In silence and stability, white dwarfs endure for time spans that dwarf the age of galaxies, cooling gradually from brilliant blue-white spheres into faint black dwarfs, although none have cooled that far yet, since the universe is too young. A white dwarf is a star supported not by fusion or thermal pressure, but by electron degeneracy pressure, a quantum mechanical force arising from the Pauli exclusion principle, which states that two electrons cannot occupy the same quantum state. In the intense, crushing gravity of the compact stellar core, electrons are squeezed so tightly that quantum physics provides the pressure needed to halt further collapse. This creates an extraordinary physical state, matter so dense that a teaspoon would weigh several tons, yet arranged in a crystalline structure where ions form a lattice, immersed in a sea of degenerate electrons. The mass of a typical white dwarf ranges from 0.6 to 1 solar masses, but its radius is only about 1% that of the Sun. As a white dwarf becomes more massive, it becomes smaller, because greater gravity compresses the star even further. This inverse mass-radius relationship is one of its most remarkable properties. At the ultimate limit, about 1/4 solar masses, known as the Chandrasekhar limit, electron degeneracy pressure can no longer support the star against gravitational collapse. If a white dwarf somehow accumulates more mass than this, perhaps through accretion from a companion star, it will trigger catastrophic carbon ignition and explode as a Type Ia supernova, leaving nothing behind. Most white dwarfs, however, live quiet, stable lives. Their atmospheres are stratified by gravity, hydrogen on top, helium beneath, and carbon and oxygen deeper still. Over time, heavy elements sink toward the interior, leaving the surface remarkably pure. Yet in some white dwarfs, the presence of metals in the atmosphere betrays active accretion, debris from asteroids, comets, or disrupted planets raining down upon the star. Such polluted white dwarfs provide unique insights into the composition of exoplanetary systems. In many cases, the elements observed, iron, calcium, magnesium, silicon, match the signatures of rocky planetary bodies. Thus, even in death, white dwarfs preserve evidence of the planetary systems they once illuminated. As white dwarfs cool over billions of years, they crystallize. Their interiors solidify into enormous spheres of electron-degenerate oxygen and carbon crystals, essentially gigantic diamonds. Some white dwarfs show evidence of this crystallization in their pulsations, while others display a sudden slowdown in cooling rates as latent heat is released. These cooling sequences allow astronomers to use white dwarfs as cosmic clocks, estimating the ages of star clusters by measuring how cool their faintest dwarfs have become. If white dwarfs represent the soft, fading end of stellar life for low-mass stars, then neutron stars represent the violent, implosive end for massive stars. Born in the catastrophic core collapse of a supernova, a neutron star is one of the densest objects in the universe, second only to black holes. A typical neutron star packs more mass than the Sun into a sphere only about 20 kilometers across. In these remnants, electrons and protons have been crushed together into neutrons, forming nuclear matter of unimaginable density. A single teaspoon would weigh billions of tons. The physics governing neutron stars is governed by neutron degeneracy pressure and nuclear forces that operate at length scales smaller than atomic nuclei. Their gravitational field is so intense that space-time curves dramatically around them. Their magnetic fields, amplified by collapse, can exceed trillions of Gauss, making neutron stars the most magnetic objects known, especially in the case of magnetars. Their rapid rotation, inherited from the angular momentum of their progenitors, can reach hundreds of revolutions per second. These rapid rotators, when beaming radiation outward, appear as pulsars, cosmic lighthouses sweeping radio beams across space. But even neutron stars that do not become pulsars remain extraordinary. Their interiors are vast laboratories of exotic physics, divided into layers that defy ordinary matter. The crust consists of a lattice of neutron-rich nuclei embedded in an ocean of degenerate electrons. Deeper in, the nuclei begin to drip neutrons, forming a superfluid neutron sea. Further still lies the core, a region where matter approaches the density of atomic nuclei and where quantum chromodynamics, including possible superfluid quark matter, takes over. We do not yet know exactly what lies in the center of a neutron star. Possibilities range from hyperons, particles containing strange quarks, to deconfined quark matter to color superconducting phases. Neutron stars thus provide a link between astrophysics and particle physics, bridging the macroscopic and quantum realms. Neutron stars display breathtaking diversity. Some emit X-ray bursts as accreted matter on their surfaces ignites. Others produce thermonuclear explosions known as type X-ray bursts. Some, in binary systems, show pulsations driven by accretion from companion stars, forming X-ray pulsars. Others, known as millisecond pulsars, rotate hundreds of times per second after being spun up by long periods of accretion from a companion. Magnetars release intense bursts of gamma rays and X-rays when their magnetic fields twist and crack the crust, producing some of the most energetic flares ever observed in our galaxy. Still others, such as isolated middle-aged neutron stars, glow faintly as they cool. The most violent events involving neutron stars are mergers, collisions between two neutron stars that spiral together under the influence of gravitational waves. When such mergers occur, the stars tear each other apart, generating a kilonova whose light carries the fingerprints of newly synthesized heavy elements. Gold, platinum, and other R-process elements are forged in these titanic collisions, then scattered across galaxies in expanding clouds. LIGO and Virgo have detected the gravitational wave signals of such mergers, while telescopes have captured the electromagnetic afterglows. These events reveal neutron stars as both destroyers and creators, annihilating themselves to build the universe's most precious elements. The fates of white dwarfs and neutron stars reflect the mass of their progenitors. Stars like the Sun end their lives gently, forming white dwarfs that cool indefinitely. More massive stars explode in supernovae and collapse into neutron stars, compact objects where quantum forces resist gravity's crushing pull. Both types of remnants preserve history. White dwarfs preserve the chemical signatures of planetary systems, while neutron stars preserve the physics of matter under extreme densities. And both continue to shape the galaxy long after their parent stars have died. White dwarfs through quiet cooling and gravitational influence, neutron stars through bursts, magnetism, and gravitational waves. They are the two great survivors of stellar death, one small, faint, enduring, the other fierce, dense, and powerful. Together, white dwarfs and neutron stars form the endpoints of stellar evolution across most of the mass spectrum, anchoring the cosmic story of birth, transformation, and collapse. They are the ancient speed demons of the cosmos, stellar corpses spun up to breathtaking velocities through the intimate and often violent embrace of a companion. Millisecond pulsars are neutron stars that rotate hundreds of times per second, their magnetic poles sweeping across space with unbelievable regularity. These cosmic lighthouses can pulse with such precision that they rival atomic clocks, drifting by less than a microsecond over many years. But their stability belies their turbulent origins. Millisecond pulsars are born old, formed in supernovae long ago, but rejuvenated through a second life, a period of mass transfer that acts like a cosmic spin-up engine, flinging them into rapid rotation. A neutron star begins its existence spinning quickly, but as it ages, magnetic braking slows it down. Over millions of years, a once rapid rotator becomes a sluggish pulsar, emitting periodic radio waves with periods of 1 second or more. But if it resides in a binary system and its companion star evolves into a red giant or subgiant that spills mass onto it, the story changes. The infalling matter transfers angular momentum to the neutron star, accelerating its rotation. Over tens or hundreds of millions of years, this process can spin the neutron star up to astonishing speeds, hundreds of rotations per second, with some exceeding 700 Hz. The fastest known, PSR J1748-224-6 AD, rotates 716 times per second, its equator moving at nearly a quarter of the speed of light. As a millisecond pulsar spins up, its magnetic field decays or is buried under the newly accreted material. This decay allows it to maintain its rapid rotation for billions of years. When accretion stops, the neutron star emerges as a stable, ultra-fast pulsar with a faint magnetic field and crystalline precision in its timing. These objects populate globular clusters in abundance, where dense stellar environments encourage binary interactions and exchange encounters. In these crowded star cities, millisecond pulsars thrive, some even acquiring new companions in gravitational encounters. Their extraordinary stability makes them essential tools in physics and astronomy. Networks of millisecond pulsars form natural gravitational wave detectors known as pulsar timing arrays. As gravitational waves pass through the galaxy, they slightly stretch and compress space-time, altering the arrival times of pulsars by tiny amounts. By monitoring a network of pulsars across the sky, astronomers can detect these distortions. In 2023, pulsar timing arrays revealed the first evidence for a gravitational wave background produced by supermassive black hole mergers. Thus, millisecond pulsars serve not only as astrophysical curiosities, but as galactic metronomes, instruments measuring the ripple of space-time itself. Yet some millisecond pulsars live far stranger lives, systems where the star that spun them up does not survive in peace, but becomes a victim of the neutron-star's relentless energy. These are the Black Widow systems, named after the spider whose females cannibalize their mates. In these binaries, the pulsar, having been spun up by accretion, turns around and begins to destroy its companion with radiation and particle winds. The companion, usually a low-mass star with less than a tenth of the Sun's mass, is gradually stripped of its outer layers as the pulsar blasts it with high-energy particles. A Black Widow pulsar rotates incredibly quickly, its rapid spin generating a fierce electromagnetic wind that bombards the companion. This wind heats the companion's star-facing side, causing dramatic brightness variations over each orbital cycle. The star becomes highly asymmetric, bloated on one side, shriveled on the other, and glowing unevenly. Over time, the pulsar evaporates its partner, stripping away layer after layer of gas until only a planet-sized remnant remains. Some companions shrink to a few thousandths of a solar mass, little more than dense, degenerate cores burned down by millennia of irradiation. The archetype of these systems is PSR B9957-T, discovered in 1988. This millisecond pulsar spins nearly 621 times per second and orbits a companion that has been whittled down to about 2% the mass of the Sun. The pulsar's wind creates a bow shock as it collides with gas being evaporated from the companion, forming a comet-like tail, trailing behind the system. As the companion dwindles, the orbital period shortens, causing tidal distortions and irregular eclipses where the pulsar's radio beams disappear behind clouds of evaporated material. Black Widow pulsars occupy an extreme niche, but an even more dramatic subset exists: the redback systems. Named after the Australian redback spider, these systems contain companions with significantly higher mass, typically 0.1 to 0.7 solar masses. Redbacks are binaries in which the companion is still actively transferring mass to the neutron-star, creating systems that can switch between accretion-powered X-ray states and rotation-powered radio pulsar states. In these transitional millisecond pulsars, astronomers can observe changes in real time as the neutron-star toggles between two modes of energy release. The system swings from spinning furiously as a radio lighthouse to flaring as an accreting X-ray source as the companion feeds it anew. Black Widows and redbacks illustrate the full life cycle of millisecond pulsars: birth in a supernova, spin up through long epochs of accretion, and eventual domination of their companions. In some Black Widow systems, the companion may ultimately be reduced to nothing at all, leaving behind an isolated millisecond pulsar, an object that once lived in a binary but consumed its partner entirely. These solitary millisecond pulsars spin on for billions of years, long after the companion that created them has vanished from existence. Beyond their dramatic astrophysical behavior, Black Widow systems provide insights into gravitational physics, binary evolution, and the equation of state of neutron stars. The precise timing of pulsars reveals the shape of the orbit, the mass of the companion, and even relativistic effects like Shapiro delay, where space-time curvature alters the travel time of pulsars. In some cases, These systems allow astronomers to measure neutron star masses with unprecedented precision. Certain black widows have revealed neutron star masses exceeding 2 solar masses, pushing the limits of nuclear physics and challenging theoretical models of dense matter. Together, millisecond pulsars and black widow systems represent two faces of neutron star evolution. One embodies stability and precision, spinning with cosmic regularity and serving as a tool for charting gravitational waves and galactic structure. The other embodies predation, cannibalism, and violent binary interaction, showing how neutron stars reshape the lives and deaths of their companions. They arise from the same origins, a once massive star collapsing into a neutron star, but diverge into radically different destinies, depending on whether their companions endure, collapse, or are devoured. These systems reveal the astonishing extremes of stellar remnants, clocks made of nuclear matter rotating hundreds of times per second, and binaries locked in cycles of accretion, evaporation, and destruction. In their rhythms and violence, they trace the story of stars long after nuclear fusion has ended, showing that even in stellar death, the cosmos remains active, dynamic, and deeply interconnected. They reside at the crossroads of theory and mystery, occupying a niche so strange that even the universe itself may rarely allow their formation. Thorne Żytkow objects, first proposed in the 1970s by Kip Thorne and Anna Żytkow, are among the most exotic hypothetical stars. Hybrid entities formed when a neutron star spirals into the core of a red supergiant without being destroyed. In this bizarre stellar union, the dense, collapsed heart of a massive star, just 20 kilometers across, finds itself embedded within the swollen, convective envelope of a supergiant hundreds of millions of kilometers wide. What results is a star that outwardly resembles an ordinary red supergiant, yet inside contains a furnace of unimaginable compactness. The formation pathway for a Thorne-Żytkow object requires finely tuned astrophysical circumstances. It typically begins in a binary system where one star has already undergone supernova collapse, leaving behind a neutron star. If its companion evolves into a red supergiant, tidal forces may draw the neutron star into the expanding envelope. Instead of colliding catastrophically or ejecting the giant's outer layers, the neutron star spirals inward through drag forces, accreting matter as it plunges toward the core. If the neutron star avoids reaching the center with too much angular momentum or too much mass accretion, it may settle into a stable orbit deep within the envelope, or merge entirely with the giant's core. Once lodged inside, the neutron star replaces the normal nuclear burning core of the supergiant. The surrounding envelope remains gravitationally bound, heated not by fusion at the center, but by the relentless accretion of material onto the neutron star. Temperatures in the envelope's inner layers can exceed anything found in ordinary stars, triggering unique nuclear reactions at the interface between the degenerate core and the surrounding plasma. These reactions are thought to produce unusual elemental signatures, particularly heavy elements like lithium, rubidium, and molybdenum, in quantities that ordinary supergiants cannot explain. Because a TGO looks so much like a normal red supergiant on the outside, identifying one requires detecting these chemical anomalies. In 2014, astronomers reported that the star HV 2112 in the Small Magellanic Cloud displayed some of the predicted chemical fingerprints, renewing interest in TGOs after decades of theoretical dormancy. Whether HV 2112 is truly a TGO remains debated, But its discovery reminded astronomers that these objects, though rare and difficult to confirm, may indeed occur in nature. If they exist, they represent a class of stellar evolution otherwise unseen. Stars powered by accretion rather than fusion, with neutron-star hearts beating beneath bloated photospheres. The fate of a TGO is equally mysterious. Some models suggest they may eventually shed their envelopes and reveal the neutron star once more. Others propose that continued accretion might push the neutron star over the Tolman-Oppenheimer-Volkoff limit, causing it to collapse into a black hole inside the star. In this scenario, the envelope might be swallowed or ejected in a final, violent outburst. In either case, TGOs remain speculative signposts of the cosmic imagination, objects that challenge our understanding of stellar interiors, binary interactions, and nuclear reactions in extreme environments. If Thorne Żytkow objects, push the boundaries of what stars can become. Then population 3 stars push our imagination back to what stars once were. They are the hypothetical first stars of the universe, born only a few 100 million years after the Big Bang, when the cosmic landscape was young, pristine, and composed almost entirely of hydrogen and helium. These primordial stars are the missing foundation of cosmic history, giants of mythic proportions whose light has long faded, yet whose influence echoes in every atom heavier than helium that now exists. Unlike later generations of stars, population 3 stars formed in an environment completely devoid of metals, elements heavier than helium, because none had yet been forged. Metal-free gas cannot cool as quickly or efficiently as enriched gas, which means the primordial star-forming clouds collapsed into much larger clumps. As a result, population 3 stars are believed to have been extremely massive, often exceeding 100 or even several hundred solar masses. Their powerful gravity pulled gas inward rapidly, giving rise to luminous, short-lived titans that burned with ferocious intensity. Their cores reached temperatures and densities surpassing anything seen in modern stars, igniting nuclear fusion through pathways that today operate only briefly or under extreme conditions. Population 3 stars produced enormous amounts of ultraviolet radiation, carving out ionized bubbles in the early universe and contributing to cosmic rayonization. Their brightness would have been extraordinary, but their lifetimes were tragically short. Just a few million years, a cosmic blink. When they died, they did so in spectacular explosions, pair instability supernovae that tore the entire star apart, leaving no remnant behind, but dispersing heavy elements across the interstellar medium for the first time. These first supernovae seeded the cosmos with carbon, oxygen, silicon, and iron, the building blocks of planets, life, and future generations of stars. Without population 3 stars, there would be no rocky worlds, no chemistry of life, no galaxies filled with diversity. They were the alchemists of the universe, forging metals from primordial gas and enriching space so that population 2 stars, metal poor but no longer pristine, could form. Later still, population 1 stars like the Sun emerged, enriched by billions of years of cosmic recycling. The challenge, however, is that no population 3 star has ever been directly observed. Their great ages mean all have long since died. Their supernova remnants, too, are impossible to isolate uniquely after billions of years of cosmic mixing. The search for them requires indirect fingerprints, chemical signatures in extremely metal-poor stars that formed shortly afterward. Some of the oldest stars in the Milky Way halo contain patterns of elements thought to reflect enrichment by only one or two population 3 supernovae. These stellar fossils allow us to infer the existence of their ancestors, much as paleontologists infer the existence of ancient animals from their footprints alone. Modern telescopes like JWST are finally pushing deep enough into the early universe to detect galaxies from the era when population 3 stars may have still existed. Their spectral signatures, if found, would show an absence of metals and an excess of ionizing radiation. Some candidate galaxies have already displayed promising characteristics: unusually hot spectra, strong hydrogen and helium lines, and a lack of heavier elements. But a definitive detection has not yet been confirmed. When it is, it will be one of the most important discoveries in cosmology, revealing the first generation of stars that brought light to the cosmic dark ages. Though separated by billions of years and radically different physical conditions, Thorne Żytkow objects and population 3 stars share something profound. Both lie at the frontier of stellar knowledge. dredge-ups inhabit the boundary between neutron-star physics and stellar structure, while population 3 stars mark the threshold between the universe's primordial simplicity and its later complexity. One shows what exotic mergers can produce. The other shows what the universe's earliest chemistry allowed. Both remind us that the cosmos is not static, but evolving, creative, and filled with extremes. They stand as chapters in a long, ongoing story of how stars live, transform, die, and give birth to new possibilities. Whether buried inside swollen giants or blazing as titanic beacons in the infant universe, these stars, real or theoretical, demonstrate the universe's limitless capacity for strangeness, power, and beauty. They stretch across the sky like ancient scars, faint, ghostly rivers of stars, tracing the memory of systems long destroyed. Stellar streams are among the most beautiful and haunting structures in the Milky Way. They are the remnants of globular clusters or dwarf galaxies that have ventured too close to the gravitational potential of the Milky Way, drawn in and torn apart by tidal forces. What remains is not a single gravitationally bound system, but a diffuse ribbon of stars orbiting the galaxy in long, graceful arcs. These streams are the skeletal remains of cosmic cannibalism, the Milky Way's long history of consuming smaller companions. To understand stellar streams, one must picture a compact cluster or small galaxy entering the Milky Way's gravitational sphere. As the object orbits, the tidal field stretches it, pulling stars from its leading and trailing edges. Over time, as the object continues its orbit, these stripped stars trace its path, forming a continuous stream that can span tens of thousands of light-years. Because these stars were once tightly bound, their orbital properties remain coherent, even after the parent structure dissolves entirely. Thus, a stellar stream acts as a fossil record of an object that may no longer exist, preserving its orbit, mass distribution, and dynamical history. Some of the most famous stellar streams include the Sagittarius stream, remnants of the Sagittarius dwarf galaxy currently being devoured by the Milky Way, and the GD1 stream, a long, narrow ribbon likely originating from a globular cluster. Others, such as the Orphan stream, Phoenix stream, and Gelum stream, stretch across the sky in faint, delicate arcs, detectable only with precise measurements from surveys like Gaia. Gaia's unprecedented astrometric catalog has revolutionized the study of stellar streams, revealing dozens of new ones and allowing astronomers to reconstruct the Milky Way's accretion history in exquisite detail. Stellar streams do more than illustrate the galaxy's violent past. They also reveal its invisible structures. Because streams act like tracer particles, they respond sensitively to gravitational perturbations. If a dark matter subhalo, a clump of dark matter with no stars, passes near a stream, it can leave gaps, wiggles, or distortions in the stream's shape. By studying these anomalies, astronomers can infer the presence of dark matter structures far too faint to detect otherwise. Thus, stellar streams provide one of the few empirical methods for probing the clumpy nature of dark matter predicted by cosmological simulations. Streams produced by globular clusters are typically thin and well-defined, because globular clusters themselves are compact and dynamically cold. Streams produced by dwarf galaxies, on the other hand, are broader and more diffuse, reflecting the larger size and lower binding energy of the progenitor. These differences allow astronomers to identify the origins of each stream, distinguishing ancient cluster remnants from the remnants of dwarf galaxies torn apart over billions of years. Each stream is a story, a minor galaxy captured and shredded, a cluster dissolved by gravitational tides, a remnant of star formation in the early universe now stretched across the Milky Way like a faint ribbon. They are the fossilized footprints of a galaxy that grew through consumption, merging and accreting to become what it is today. If stellar streams represent the aftermath of cluster destruction, then open star clusters represent the beginning of the story, a stellar family in its youth. These clusters are loose, gravitationally bound associations of a few dozen to a few thousand stars, all formed from the same molecular cloud. They represent the typical environment in which most stars, including the Sun, are born. Unlike the dense, ancient globular clusters, open clusters are young, fragile, and ephemeral. Their stars share a common age and chemical composition, making them crucial laboratories for understanding star formation and stellar evolution. Open clusters form in the dense regions of giant molecular clouds when those clouds collapse under their own gravity. Turbulence, magnetic fields, and local density fluctuations guide this collapse, fragmenting the cloud into cores where protostars ignite. Much of the mass of the original cloud disperses quickly, blown away by winds and radiation from young, massive stars. What remains are the brightest and most centrally concentrated stars, the open cluster, embedded in a great expanse of gas and dust. Some of the most famous open clusters are readily visible to the naked eye. The Pleiades, a brilliant collection of blue hot stars cloaked in faint nebulosity. The Hyades, a sprawling V-shaped cluster near Taurus. And the Beehive cluster, shimmering faintly in Cancer. These clusters offer astronomers a snapshot of star formation at different ages. The Pleiades, only around 100 million years old, still contain the hot B-type stars that will soon burn out. The Hyades, several hundred million years older, show more evolved stars and fewer massive members. Open clusters are short-lived on cosmic timescales. Their binding energy is weak, and they are easily disrupted by tidal forces as they orbit the Milky Way. Encounters with giant molecular clouds, spiral arms, or simply cumulative gravitational scattering gradually strip stars from the cluster. Over hundreds of millions of years, most open clusters dissolve entirely, their stars dispersing into the galactic disk. Even the Sun, likely formed in such a cluster, long since scattered, its siblings now indistinguishable among billions of stars. But while they last, open clusters serve as stellar laboratories. Because all stars in a cluster share the same age, astronomers can construct precise color magnitude diagrams that reveal stellar evolution in action. By comparing the positions of stars in the diagram with theoretical models, astronomers can determine cluster ages with remarkable accuracy. Open clusters also reveal insights into star formation efficiency, binary star populations, rotational evolution, and the effects of stellar feedback on surrounding gas. Chemical studies of open clusters trace the chemical enrichment of the Milky Way's disk. As new generations of clusters form, their metallicities gradually increase, reflecting the accumulation of heavy elements synthesized in prior generations of stars. Thus, studying open clusters of different ages reconstructs the history of star formation, nucleosynthesis, and galactic chemical evolution across billions of years. Open clusters also give rise to some of the most interesting dynamical processes in stellar astrophysics. Mass segregation, where heavier stars sink toward the cluster center while lighter stars migrate outward, occurs naturally through gravitational interactions. Over time, this creates dense central regions where stellar collisions or mergers may occur. In some clusters, blue stragglers form, stars that appear younger and hotter than they should be, likely rejuvenated through mass transfer or merger events. From birth to dissolution, an open cluster represents a universe in miniature. Star formation, stellar evolution, dynamical interactions, mass loss, and eventual dispersal into the wider galaxy. Their stars drift outward until the cluster dissolves, contributing to the galactic disk. Over billions of years, these dispersed stars can form large-scale structures, streams, moving groups, or associations that preserve traces of their original shared origin, echoing the young cluster long after it has faded away. Thus, stellar streams and open clusters are connected at opposite ends of a cosmic timeline. One is the newborn family of stars still bound by youth and proximity. The other is the stretched-out remnant of a once coherent system long since unbound. Open clusters dissolve, stellar streams record their dissolution. Together they form a narrative of structure, memory, and transformation within the Milky Way. They hang like ancient lanterns in the halo of the Milky Way, densely packed and glimmering with the light of hundreds of thousands of stars. Globular clusters are among the oldest surviving structures in the universe, relics from a time when galaxies were first assembling. Each one is a spherical swarm of stars, so tightly bound that a single cubic light-year near the core may contain dozens of suns. These clusters orbit the galaxy far above and below its disk, moving through the halo in sweeping elliptical orbits that carry them across regions untouched by star formation for billions of years. Their stars, nearly as old as the universe itself, serve as living fossils that preserve the chemistry, dynamics, and history of the early cosmos. A typical globular cluster contains several 100,000 stars, though some, like Omega Centauri or Maiol 2 in Andromeda, contain millions. Their stars are almost exclusively old, metal-poor population 2 stars. The extremely low metal content is a signature of their ancient age, reflecting a time before supernovae had significantly enriched the interstellar medium. Many globular clusters formed more than 12 billion years ago, only a few hundred million years after the Big Bang. They represent one of the earliest modes of star formation, emerging before the Milky Way itself had assembled into a coherent disk. The structure of a globular cluster is determined by gravity and time. Over billions of years, gravitational interactions between stars lead to mass segregation. Heavier stars sink toward the cluster center, while lighter stars migrate outward. This process creates extraordinarily dense cores where stellar collisions and mergers can occur. In fact, these dense regions are fertile territory for forming exotic stellar objects such as blue stragglers, stars that appear anomalously young and bright, likely rejuvenated by mergers or mass transfer between binary companions. These collisions are not violent enough to destroy stars, but powerful enough to combine them, producing unexpected populations in environments otherwise dominated by ancient, dying suns. Globular clusters also act as factories for compact objects. Their dense stellar environments encourage the formation of close binaries, neutron-star systems, millisecond pulsars, and even potential black hole binaries. In the cores of some clusters, dozens of millisecond pulsars spin with precise rhythms, spun up by past episodes of accretion from companion stars. These pulsars act as probes of the cluster's gravitational field, mapping its internal mass distribution with exquisite precision. Dynamically, globular clusters evolve through two-body relaxation, a slow exchange of energy between stars that gradually reshapes the cluster over billions of years. Some clusters have undergone core collapse, contracting their central regions to incredibly high densities. Others show evidence of multiple stellar populations, indicating that they may have formed in multiple bursts of star formation, or that they may be the remnants of dwarf galaxies captured by the Milky Way. Their orbits tell the story of galactic archaeology. Some globular clusters move in coherent streams, tracing the shredded remnants of ancient dwarf galaxies devoured by the Milky Way. Others have retrograde orbits, suggesting they originated outside the galaxy entirely. Through these motions, globular clusters reveal the hierarchical nature of galactic formation. The Milky Way built not through isolated collapse, but through relentless mergers and acquisitions. Yet globular clusters are not eternal. As they orbit the galaxy, tidal forces from the Milky Way's disk and bulge gradually strip stars from their outer layers. These stripped stars form tidal tails that stretch across tens of degrees of sky, the beginnings of stellar streams. Over billions of years, some globular clusters dissolve entirely, their stars dispersing into the halo. But the most massive clusters, bound tightly by gravity, remain intact for the lifetime of the universe. They are the cosmic monasteries of the Milky Way, isolated, ancient, self-contained, and infused with the quiet glow of primordial starlight. From these dense and ancient star cities, we turn to one of the ultimate endpoints of stellar evolution, the stellar mass black hole. If a neutron star is the crushed remnant of a once massive star, a stellar mass black hole is the final step, an object so dense that nothing, not even light, can escape its gravity. These black holes form when stars of roughly 20 solar masses or more exhaust their nuclear fuel and collapse under their own immense weight. In a supernova, or sometimes a failed supernova, the core collapses past the neutron-star stage, its matter compressed beyond the limits of nuclear physics, leaving behind a singularity enveloped by an event horizon. A stellar mass black hole is defined not by what it contains, but by what it hides. The event horizon marks the boundary beyond which information cannot escape. Inside, classical physics breaks down. General relativity predicts a singularity, an infinitely dense point where space-time curvature becomes infinite. Whether such a singularity truly exists, or whether quantum gravity resolves it, remains one of the deepest mysteries in physics. Outside the event horizon, however, the gravitational influence of a stellar mass black hole is perfectly well defined, shaping the orbits of nearby stars, bending light, and funneling infalling matter into radiant accretion flows. Because black holes emit no light, they are detected through their interactions. In binary systems, a black hole may pull material from a companion star, forming a luminous accretion disk that radiates in X-rays. These systems, black hole X-ray binaries, exhibit powerful jets, flickering variability, and dramatic outbursts as the accretion flow reorganizes. Their X-ray spectra reveal the conditions of matter spiraling toward the event horizon, heated to millions of degrees as it loses angular momentum and plunges inward. Some black hole binaries, such as Cygnus X1, were among the first strong candidates for black holes ever discovered. Other black holes are found through their gravitational dominance. Stars orbiting an unseen mass, such as those near the galactic center, betray the presence of a compact object. In recent years, gravitational wave detectors like LIGO and Virgo have revolutionized black hole astronomy by detecting mergers of stellar mass black holes. These mergers produce transient ripples in space-time, detectable across billions of light years. The black holes involved often have masses between 10 and 50 solar masses, though some events have revealed black holes in the so-called pair instability mass gap, where traditional stellar evolution theory predicts no remnants should exist. These discoveries challenge existing models of stellar collapse, binary evolution, and metal-poor star formation. Stellar mass black holes also offer insights into the population of massive stars across cosmic time. The mass distribution of black holes depends on metallicity. Metal-poor stars lose less mass through winds, allowing them to form heavier black holes when they collapse. Thus, black holes in the early universe may have been significantly more massive than those forming today. This has implications for gravitational wave astronomy, the growth of supermassive black holes, and the evolution of galaxies. Not all stellar mass black holes reside in binaries. Many wander the galaxy alone, silent and invisible. Some may pass through interstellar gas, creating faint accretion signatures detectable only with sensitive X-ray observatories. Others may drift through the galactic disk unnoticed until they lens background stars through gravitational microlensing. Such events reveal the mass of the unseen object and offer one of the few ways to detect isolated black holes directly. Despite their fearsome reputation, stellar mass black holes are straightforward in their essence. They are the remnants of massive stars that exhausted all avenues of pressure support. They grow by accretion and by merging, contributing to the cosmic cycle of collapse and structure formation. Each one is a testament to the life of a massive star, preserving its core collapse in the form of an object that warps space-time around it. Globular clusters and stellar mass black holes may at first seem unrelated. One ancient and diffuse, the other end, state compact, but they are deeply intertwined. Globular clusters may host black holes at their cores. Some may have formed intermediate mass black holes through runaway mergers. Others may eject their black holes through dynamical interactions. Stellar mass black holes, in turn, record the deaths of the earliest massive stars, stars that may have once lived in the very clusters that still orbit the galaxy today. Together, they represent the beginning and end of stellar life on a grand scale. Clusters where stars are born in ancient epochs, and compact remnants where the most massive stars end in gravitational collapse. Between them stretches the story of the universe's evolution, written in stars long dead and structures still dazzling. They sit at the hearts of galaxies like dark monarchs, invisible yet overwhelmingly influential, ruling the dynamics of entire star systems through gravity alone. Supermassive black holes, SMBHs, are among the most enigmatic structures in the universe, with masses ranging from millions to billions of times that of the Sun. Their event horizons can span the size of our solar system, yet they hide within galactic cores, dense, compact, and utterly dark, except when accreting matter. Every large galaxy known hosts a SMBH at its center, including the Milky Way, whose own central giant, Sagittarius A, weighs roughly 4 million solar masses. These objects govern the structure and evolution of galaxies, shaping star formation, regulating gas flows, and influencing cosmic history on vast scales. An SMBH is defined not simply by mass, but by its deep gravitational well, a region where space-time is curved so extremely that any object crossing the event horizon is forever lost to the observable universe. Yet despite their lethargic, massive nature, these giants are not passive. When gas, dust, or stars venture too close, they are stretched, heated, and torn apart in brilliant emissions of energy. Accreting SMBH's power, active galactic nuclei AGN, quasars, blazars, and radio galaxies, some of the brightest sustained beacons in the universe. Quasars can outshine entire galaxies, their brilliance fueled by the conversion of gravitational potential energy into radiation as matter swirls at a significant fraction of light speed before disappearing. The formation of SMBHs remains one of astrophysics' most compelling mysteries. How did objects so massive assemble so quickly in the early universe? Observations by JWST revealed quasars less than 1 billion years after the Big Bang, containing black holes already weighing hundreds of millions of solar masses. Such rapid growth challenges our understanding of stellar evolution. One possibility is that early black holes began life not as the modest remnants of stars, but through direct collapse of primordial gas clouds, enormous metal-poor clouds collapsing under gravity without fragmenting into stars. Another possibility is that dense, early star clusters collapsed into intermediate mass black holes that then merged repeatedly. A third possibility is more radical still, that some SMBHs were seeded by an entirely different population of objects, primordial black holes left over from the first fractions of a second of cosmic time. SMBHs also regulate their galaxies through a delicate balance of feeding and feedback. When gas spirals inward, the SMBH brightens dramatically, and its radiation and jets heat or expel the surrounding gas. This feedback can shut down star formation, sculpt galactic structures, and even drive massive outflows that sweep clean entire regions of interstellar material. The interplay between SMBH growth and galactic evolution is so tightly linked that astronomers see a consistent relationship between the massive SMBHs and the velocity dispersion of stars in their galactic bulges, the famous M-sigma relation. Somehow, galaxies and their central black holes grow together, influencing one another across billions of years. SMBHs also host some of the universe's most violent events. A star straying too close may be torn apart in a tidal disruption event, its materials stretched into a luminous arc, flaring in X-rays and UV light as it spirals inward. In galaxy mergers, SMBHs themselves can form binary systems, spiraling toward each other over millions of years before merging in cataclysmic bursts of gravitational waves. The low-frequency gravitational wave background, recently detected through pulsar timing arrays, likely originates from thousands of such SMBH binaries throughout cosmic history. Yet even these giants are overshadowed in mystery by an even more ancient and elusive class of objects, primordial black holes, hypothetical remnants of the universe's earliest moments. Unlike stellar or supermassive black holes, primordial black holes, PBHs, were not formed from collapsing stars, but may have formed from density fluctuations in the first second after the Big Bang. In those chaotic moments, the universe was filled with extreme pressures and temperatures, and small regions with slightly higher density could, in principle, collapse directly into black holes. Depending on the magnitude of the initial fluctuations, these PBHs could span enormous mass ranges, from microscopic masses smaller than asteroids to thousands of solar masses. Unlike conventional black holes, which require stars, primordial black holes would be truly ancient, older than any star, older even than galaxies. If they exist, they would be relics of the universe's birth, and their mass distribution would preserve information about early cosmological conditions. Some theories propose that PBHs could make up a significant fraction of dark matter, filling galactic halos with invisible compact objects. Microlensing surveys have searched for such objects, and while many constraints have ruled out PBHs as the sole dark matter component in most mass ranges, tantalizing windows remain, especially around asteroid-sized black holes or intermediate mass candidates. The evaporation of primordial black holes via Hawking radiation also offers a unique observational signature. Extremely low-mass PBHs, those with masses less than about 1 trillion tons, would evaporate completely over the age of the universe, ending their lives in explosive bursts of high-energy gamma rays. This evaporation could contribute to cosmic backgrounds or produce observable transient events. Larger PBHs would still exist today, evaporating slowly or not at all at scales where Hawking radiation becomes negligible. The possibility that some gravitational wave detections, particularly black hole mergers involving unexpectedly high masses or strange mass ratios, might be signatures of PBHs, has reignited interest. If even a small fraction of LIGO-Virgo detections arise from primordial origins, it would dramatically reshape our understanding of cosmic structure formation. PBHs could serve as seeds for early SMBHs, explaining how such massive objects appeared so quickly in the young universe. They could also structure dark matter halos or provide clues about inflationary physics, linking cosmology, particle physics, and gravitational astrophysics in profound ways. Even the mass spectrum of PBHs could reveal the shape of primordial density fluctuations from the early universe. A universe that produced PBHs would have experienced brief departures from perfect uniformity, possibly due to inflationary spikes, phase transitions, or other exotic physics. Thus, the search for PBHs is not merely a search for black holes, it is a search for new physics. In many ways, supermassive black holes and primordial black holes bracket the cosmic narrative of gravitational collapse. SMBHs are the universe's grand architects, assembled over billions of years, regulating the structure of galaxies and powering quasars. PBHs, if they exist, are the universe's original building blocks, formed before galaxies, before stars, before atoms. One type is born from the deaths of stars and the evolution of galaxies. The other may be born from the universe's first heartbeat. Both remain central to some of the deepest questions in astrophysics. How do SMBHs grow to such vast scales? Do PBHs exist? And if so, what do they tell us about the infancy of the universe? Could PBHs explain dark matter or seed the earliest galaxies? The answers to these questions will reshape our understanding of cosmic origins. Together, these two classes of black holes, one confirmed and colossal, the other hypothetical and primordial, represent the extremes of gravitational power, from the cores of galaxies to the first fractions of cosmic time. They map the full spectrum of what gravity can do, from shaping galactic architecture to encoding the physics of the Big Bang. They form wherever gravity captures matter and forces it into rotation around a compact object. Great luminous whirlpools suspended in space, glowing with the heat of spiraling gas. Accretion disks are among the most important structures in high-energy astrophysics, serving as engines that transform gravitational potential energy into radiation. Around black holes, neutron stars, and white dwarfs alike, these disks act as cosmic furnaces, heating gas to millions of degrees and producing intense emissions of X-rays, ultraviolet radiation, and sometimes even visible light. They are the crossroads where matter meets extreme physics, where turbulence, magnetism, and relativity weave together into one of the universe's most dynamic phenomena. An accretion disk forms when matter, rather than falling directly onto a compact object, carries angular momentum. This angular momentum keeps the material from collapsing straight inward. Instead, it spirals around the compact object in a flattened, rotating disk. Viscous forces, mediated not by molecular motion, but by magnetic turbulence, such as the magnetorotational instability, MRI, cause the inner regions of the disk to move faster than the outer ones. This differential rotation triggers turbulence that transports angular momentum outward, allowing matter to drift inward. As matter spirals toward the compact object, gravitational potential energy converts into heat, making the disk extraordinarily luminous. Around a neutron star or white dwarf, the disk glows brightly but remains outside a solid surface. In these systems, the infalling gas eventually crashes into the stellar surface or onto a magnetic pole, releasing an additional burst of energy. Around a black hole, however, there is no surface, only an event horizon. The gas in the inner disk accelerates to relativistic speeds and becomes so hot that it emits X-rays before crossing the point of no return. The inner region of the disk, known as the innermost stable circular orbit, ISKO, depends on the black hole's spin. A rapidly spinning black hole allows matter to orbit closer before plunging inward, increasing efficiency and luminosity. A non-spinning black hole has a farther-out ISKO, making the accretion process less efficient. The energy conversion efficiencies of these disks are astonishing. While nuclear fusion converts less than 1% of a star's mass into energy, accretion onto a black hole can convert up to 40% of the infalling mass into radiation. This is why quasars, powered by supermassive black holes with accretion disks, are the most luminous steady objects in the universe. Entire galaxies can be outshone by a single accretion disk surrounding a supermassive black hole, the light fueled by gas swirling around an event horizon. The physics within an accretion disk is a symphony of extremes. Temperatures in the inner disk can exceed millions of degrees, hot enough to ionize atoms fully and produce strong X-ray emissions. Magnetic fields thread the disk, channeling energy and shaping turbulence. The MRI acts as a powerful dynamo, amplifying magnetic fields and transporting angular momentum outward. Radiation pressure can dominate over gas pressure in the inner regions, leading to instabilities that cause oscillations, outbursts, or dramatic variability. These processes produce flickering light curves and quasi-periodic oscillations that encode information about the disk's structure and the compact object at its center. Some disks launch outflows, winds driven by heat or radiation pressure that carry away angular momentum. Others produce collimated jets that shoot outward at relativistic speeds. These jets, powered by magnetic fields anchored in the disk or threading the black hole itself, are among the most spectacular sights in the universe. Jet formation remains an active area of research, but leading models include the Blandford-Zernike mechanism, in which magnetic fields tap into a rotating black hole's energy, and the Blandford-Payne mechanism, in which magnetic fields fling matter outward from the disk's surface. These jets give rise to the phenomenon known as relativistic beaming, where radiation emitted by rapidly moving matter becomes concentrated along the direction of motion. When a jet travels close to the speed of light, its emitted light becomes Doppler boosted, brightened enormously for observers aligned with the jet, and dimmed for those looking from the side or behind. This beaming effect explains why blazars, active galactic nuclei whose jets point toward Earth, appear far brighter and more variable than ordinary quasars. The jet's energy is not intrinsically greater, it simply appears amplified due to relativity. Relativistic beaming affects not only brightness, but also time. Variability within a beamed jet appears faster, compressed by Doppler effects. A flare occurring over several days in the jet's rest frame may appear to last only hours to an observer. Frequencies shift as well. Radiation emitted at radio wavelengths in the jet's rest frame might be observed as optical or even X-ray radiation once it has been boosted by relativistic motion. Even at stellar scales, relativistic jets form astonishing structures. Microquasars, X-ray binaries with stellar mass black holes, produce jets that mimic the behavior of supermassive black holes on much smaller scales. In systems like GRS 1915-1105, jets exhibit rapid oscillations and enormous energy release. The SS-433 system showcases relativistic jets precessing like a wobbling gyroscope, their emission lines blue-shifted and red-shifted by velocities approaching a quarter of the speed of light. In neutron-star systems, jets can be equally powerful, though their formation is influenced by the presence of a quiche, solid surface, and intense magnetic fields. Even white dwarf systems can produce jets under the right conditions. Across all systems, the essential ingredient is the accretion disk. It feeds, organizes, and powers the jet, making the disk-jet connection one of the central pillars of high-energy astrophysics. Relativistic beaming also plays a role in gamma-ray bursts, where ultra-relativistic jets from collapsing massive stars or merging compact objects beam their energy into narrow cones. If Earth lies within the cone, the burst appears extraordinarily bright. If not, the event may go unnoticed entirely. This angular dependence explains why the universe contains far more GRB events than those we detect. Accretion disks and relativistic beaming together define much of the high-energy universe. Disks transform gravity into radiation, while beaming transforms motion into dazzling luminosity. They are the engines and the amplifiers of cosmic power. The disk governs how matter spirals inward. The jet shows how matter and magnetic energy can be flung outward. Without accretion disks, quasars would be dark, X-ray binaries quiet, and gamma-ray bursts impossible. Without relativistic beaming, the universe would appear far dimmer, its most extreme events hidden behind the veil of unfocused emission. Together, they reveal a universe that does not merely collapse under gravity, but channels that collapse into luminous displays. The physics of extreme rotation, magnetism, radiation, and space-time curvature converge in these two phenomena, making them indispensable to understanding how black holes and neutron stars interact with their environments. In their brightness, variability, and power, accretion disks and beamed jets illuminate the universe's most violent and extraordinary mechanisms. Gravity does not simply pull on matter, it pulls on time and light themselves. Near-compact objects, white dwarfs, neutron stars, and especially black holes, gravity becomes so intense that it stretches space-time, altering the flow of time and draining energy from escaping radiation. This phenomenon, known as gravitational redshift, is one of the most profound predictions of general relativity. It arises whenever light climbs out of a gravitational well. Its frequency decreases, its wavelength lengthens, and its color shifts toward the red end of the spectrum. In weak fields, like Earth's, the effect is subtle. In strong fields, near neutron stars, or the event horizon of a black hole, it becomes unmistakable, a direct imprint of warped space-time upon the photons that escape it. To understand gravitational redshift, imagine a photon emitted from deep within a gravitational well. Light carries energy, and climbing outward requires work, just as a stone thrown upward loses kinetic energy as it rises. But while a stone slows down, a photon cannot. It always moves at the speed of light. Instead, it loses energy by lowering its frequency. The deeper the gravitational well, the more energy drained and the greater the redshift. This effect has been measured in laboratories on Earth using atomic clocks placed at different elevations, but near compact objects, it becomes a dominant part of their spectral signatures. In white dwarfs, gravitational redshift reveals the star's mass and compactness. A photon emitted from the dwarf's surface climbs through a gravitational well so deep that its spectral lines shift measurably, tens of kilometers per second in apparent velocity. This redshift allows astronomers to weigh white dwarfs precisely, confirming the predictions of electron degeneracy pressure and the mass-radius relationship. Near neutron stars, the effect becomes far more dramatic. Their surfaces are so compact that gravitational redshift can remove a significant fraction of a photon's energy. X-ray bursts, thermonuclear flashes on neutron star surfaces show redshifted lines that hint at the crushing gravity of matter compressed to nuclear densities. But it is near black holes that gravitational redshift becomes overwhelming. At the event horizon, time appears to stop relative to a distant observer. Light, attempting to escape, becomes infinitely redshifted, its wavelength stretching without limit until it fades from view entirely. This is not an optical illusion. It is the structure of space-time itself. Material spiraling into a black hole emits radiation as it heats, but as it approaches the event horizon, its light becomes stretched and distorted. Observers see infalling matter slow, dim, and redden, appearing to freeze just outside the horizon in a ghostly, fading glow. This eternal descent is how the outside universe perceives matter approaching a black hole, its final signals smeared out across time by gravity. Gravitational redshift is not merely a curiosity. It is a tool for probing the nature of compact objects and the curvature of space-time. The profiles of spectral lines, the timing of pulsars, the shape of accretion disk emission, and the shadow of a black hole itself all carry its signature. The Event Horizon Telescope image of M87 revealed not merely a ring of emission, but one warped asymmetrically by gravitational redshift and light bending. General relativity is written into the glow around the event horizon. Yet gravitational redshift becomes even more intriguing when paired with objects that challenge our assumptions about how black holes form and grow. One such object is the supermassive black hole candidate at the heart of NGC 1277, a galaxy whose existence has upended traditional notions of black hole galaxy coevolution. NGC 1277 is a lenticular galaxy in the Perseus cluster, compact and old, a relic from the early universe. But what makes it astonishing is the mass of the black hole at its center, estimated at one point to be an incredible 17 billion solar masses, nearly 60% of the galaxy's total stellar mass. In most galaxies, including the Milky Way, the central black hole comprises a tiny fraction, typically less than 1% of the galaxy's mass. This relationship, formalized in the M-sigma relation, demonstrates a tight correlation between black hole mass and the velocity dispersion of stars in the galactic bulge. Somehow, galaxies and their black holes grow in tandem, linked by feedback processes that regulate star formation and black hole accretion. But NGC 1277 appears to break this law spectacularly. Its black hole is far too massive for the size of the galaxy surrounding it, like a seed that grew into a giant tree while the forest remained stunted. This overmassive black hole raises profound questions. Did NGC 1277 once contain far more stars, stripped away by gravitational encounters in the dense Perseus cluster? Or did it form uniquely early, before the standard galaxy black hole relationship solidified? It may be a relic galaxy, a fossil from the universe's first billion years, formed in a rapid burst and then left untouched by mergers or significant star formation. In this scenario, its central black hole also formed early, possibly seeded by an unusually massive black hole created from a direct gas collapse, or even, as some speculative theories suggest, from a primordial black hole. Observations from the Hubble Space Telescope, the Hobby-Eberly Telescope, and integral field spectroscopy have attempted to refine the black hole's mass. Some estimates have reduced it to around 5 billion solar masses, still enormous and still anomalous for a galaxy as small as NGC 1277. Whether 5 billion or 17 billion, the central object remains one of the most extreme SMBHs known. The environment around NGC 1277's black hole provides a unique laboratory for extreme gravitational physics. Stars orbit at incredible speeds near the core, their spectral lines broadened and skewed not only by Doppler shifts, but also by gravitational redshift from the deep potential well. Infrared measurements reveal stellar motions that can only be explained by an immense central mass confined to a region no larger than a few light hours across, consistent with a supermassive black hole, but far too dense for any cluster of stars. Here, gravitational redshift does more than mark the presence of intense gravity. It acts as a ruler, measuring the curvature of space-time itself. The existence of such an overmassive black hole has implications for galaxy evolution models. If NGC 1277 is a relic of the early universe, its black hole may preserve information about the earliest SMBH seeds. Did the universe produce black holes of tens of thousands of solar masses at once, allowing rapid growth? Did dense gas clouds collapse directly into black holes without forming stars? Did early galaxies form stars inefficiently around their black holes, leaving the central mass disproportionately dominant? NGC 1277 may hold answers to these questions, offering a window into the childhood of the cosmos. At the intersection of gravitational redshift and extreme black hole mass lies a deeper truth. Compact objects bend not only light, but also our understanding of cosmic history. Gravitational redshift reveals the invisible geometry of space-time and confirms predictions of general relativity. Overmassive black holes, like the one in NGC 1277, challenge the classical narrative of galaxy growth. Together, they demonstrate the richness of the universe's extremes, where gravity stretches light, where time itself slows, and where galaxies carry ancient secrets encrypted in the motions of their stars. They are the quiet ones, so faint, so unassuming, that for decades, astronomers did not even realize they existed. Quiescent black hole systems are the dormant remnants of cosmic violence. Stellar mass black holes paired with companion stars in wide, dim binaries where accretion has slowed to an almost imperceptible trickle. Unlike their more flamboyant cousins, the bright X-ray binaries that blaze furiously when gas funnels inwards at high rates, quiescent systems spend most of their lives in silence. They shine only faintly in X-rays, emit weak radio signals, and reveal their presence primarily through the gravitational tug they exert on their companions. Yet in their quietude lies some of the most valuable information about black holes: their true masses, their spins, their distribution in the galaxy, and the evolutionary pathways that lead from massive stars to compact remnants. A quiescent black hole system forms when a once active X-ray binary exhausts or stabilizes its supply of infalling gas. The companion star may have shrunk, cooled, or evolved away from mass transfer. The accretion disk, formerly bright and turbulent, becomes thin, cool, and geometrically faint. The inner region of the disk may evaporate entirely, replaced by a radiatively inefficient accretion flow, a hot, tenuous plasma spiraling inward with little light emission. Instead of glowing brightly, the black hole feeds now in slow motion, swallowing small quantities of gas without generating the intense radiation seen in outbursting systems. In this low luminosity state, the accretion efficiency collapses, and much of the gravitational energy becomes locked in the flow rather than radiated. These systems are astrophysical ghosts. They do not call attention to themselves through flares or jets or eruptive behavior. They masquerade as ordinary stars until precise radial velocity studies reveal orbital wobbles far too large to be caused by any visible companion. Only then does the truth emerge. The unseen companion is a stellar mass black hole, its mass measured through the motions of the living star beside it. Some of the best mass determinations for black holes come from quiescent systems, where the absence of a bright accretion disk means starlight is not overwhelmed by radiation. The companion's spectral lines can be tracked with exquisite detail, allowing astronomers to weigh the black hole with remarkable precision. Quiescent black holes also play a crucial role in understanding the mass gap, the puzzling dearth of compact objects between roughly 2.5 and 5 solar masses. Neutron stars appear to top out around 2.3 solar masses, while most known black holes leap suddenly to around 2 solar masses or more. Whether this gap is real or simply observational bias has been debated for years. Quiescent systems may hold the key. They are unbiased by selection effects that favor bright, accreting black holes. Their black holes represent the underlying population rather than just the flamboyant tip of the iceberg. Some quiescent systems have revealed black holes potentially lying within the mass gap, challenging long-held assumptions about supernova physics. Reconstructing the lives of these systems offers insight into binary evolution. Many quiescent black hole binaries began in fierce mass transfer episodes that spun up the companion star, stripped its atmosphere, or triggered runaway outbursts. Now, billions of years later, the drama has subsided. The black hole remains a silent anchor, faintly accreting from stellar winds or from residual disk material, while the companion star continues to orbit in gravitational obedience. Their quiescent state is not permanent. Instability in the disk may someday reignite an outburst, returning the system briefly to brilliance before it fades again. If quiescent systems represent black holes at rest, then microquasars represent black holes in fury, compact objects unleashing relativistic jets as dynamic and powerful as those from supermassive black holes, but on stellar scales. A microquasar is a binary system containing a stellar mass black hole or neutron-star accreting gas at high rates, generating hot accretion disks and launching jets that move at significant fractions of the speed of light. They are miniature versions of the quasars that shine at the centers of distant galaxies, but far closer and far more rapidly evolving. The name microquasar reflects similarities that extend far beyond superficial appearance. Both quasars and microquasars possess accretion disks, coronae of hot plasma, and relativistic jets. Both exhibit outbursts, variability, and spectral states governed by the geometry and rate of accretion. Both produce radio lobes, shocks, and knotty jet structures that move outward as discrete packets of plasma. In fact, microquasars often change states on human timescales, days, weeks, or months, whereas quasars evolve over millennia or longer. Because microquasars are smaller and faster, they serve as time-compressed laboratories for studying accretion and jet formation. Perhaps the most famous microquasar is GRS 1915-105, a system whose black hole displays some of the most extreme variability in the known universe. Its X-ray light curve dances with complex patterns driven by instabilities in its accretion disk. Its jets, launched in repeated bursts, exhibit apparent superluminal motion, an illusion created by relativistic beaming when the jet's velocity approaches the speed of light. Another iconic system, SS-433, launches jets that precess like a cosmic gyroscope, producing emission lines shifted by tens of thousands of kilometers per second. These shifts reveal not only velocity, but the orientation and wobble of the jet, allowing astronomers to reconstruct the three-dimensional geometry of the system. The mechanics of jet launching are deeply tied to magnetic fields. The accretion disk, threaded by magnetic lines, acts as a dynamo. These magnetic structures twist, stretch, and channel energy outward. In some models, jets draw power not only from the disk, but also from the rotation of the black hole itself. The Blandford-Zerniak mechanism proposes that magnetic fields anchored in the disk can extract rotational energy from the event horizon, flinging matter outward in collimated streams. Whether the disk or the black hole contributes more power remains a subject of active debate, but microquasars are crucial to unraveling this question. Their rapid variability allows continuous monitoring, revealing correlations between disk states and jet activity. When a microquasar transitions into a low hard state, the disk becomes truncated and a compact jet brightens in radio wavelengths. During transitions to the high soft state, the disk extends inward, the jet weakens or disappears, and X-ray emissions change dramatically. These cycles are miniature analogues of the behavior seen in active galactic nuclei, where accretion state transitions occur on timescales too long for human observation. Microquasars, therefore, act as fast-forward versions of quasars, systems where astrophysicists can watch in real time the processes that govern black hole feeding and outflow. Microquasars also influence their surroundings. Their jets inject energy into the interstellar medium, creating cavities, shocks, and radio lobes on parsec scales. These interactions, though smaller than those of radio galaxies, follow the same physical principles. In some systems, the jets inflate bubbles of hot gas detectable in X-rays, demonstrating how even a single stellar mass black hole can sculpt its local environment. The contrast between quiescent black holes and microquasars illustrates the full dynamic range of black hole accretion. In one state, the black hole is nearly invisible, detectable only through gravitational influence. In the other, it becomes a cosmic engine, converting mass into light and motion at extraordinary efficiencies. What changes is not the black hole itself, its mass, its spin, its event horizon, but the flow of matter around it. Accretion is the lifeblood of black hole activity. In abundance, it creates blazing disks and relativistic jets. In scarcity, it yields quiet faintness, broken only by the whisper of low-level infall. Together, quiescent systems and microquasars show that black holes are not static objects, but participants in an evolving dance with their environments. They sleep, they awaken, they flare, and they fade. They can be silent shadows for centuries and then erupt into brilliance for months. Their lives are not singular events, but cycles shaped by disks, companions, magnetic fields, and the physics of plasma flowing near the edge of space-time. The diversity of their behavior reflects the richness of the cosmos itself.